Okay, I'd like to finish up section 11.3 in this video and then possibly 11.5. We're on problem 42. Let the sample space for an experiment be the set of counting numbers 1 through 15 and select a number at random from S. A is the event that the number selected is even. Okay, so here's set A. B is the set that the event that the selected number is a multiple of 4. Okay, so here's B. C is the event that the selected number is a prime number. Okay, so here's C. Okay, remember, a prime number is one that's divisors are only 1 in itself. Okay, so 2 is the only even prime number. Part A, what is the probability of B? Okay, well, there's 3 things in B. 15 things total in the sample space, so 3 over 15 is 1/5. What is the probability of A and B? Okay, so for us to select a number that is in both A and B, let's see, 4, 8, and 12. All 3 of those numbers are even numbers there. So 3 over 15 is 1/5. Okay, so that didn't change anything. Part C, what is the probability of B and C? Okay, so B and C, 4, 8, 12, neither one of those are in C, so that'd be 0, a 0% chance. Part D, what is the probability of B given A? Okay, the probability of B given A is the probability of B and A divided by the probability of A. Remember, whatever event you're given, you're going to be dividing that by the probability of that event in the formula. Okay, so the probability of B and A is 3 over 15, we said, which is equal to the probability of A and B. Okay, so 3 over 15 divided by the probability of A. There are 7 things in A. 7 over 15. Okay, flip the denominator and the 15s are going to cancel. So 3 over 7. Remember that a conditional probability means that your sample space is reduced in size. So given event A, okay, these 7 numbers, 7, what is the probability of B? Okay, well, 3. 3 divided by 7. We could have went right to the answer. Okay. Part E, what's the probability of A given C? Okay, so the probability of A and C divided by the probability of C. Probability of A and C, 2. Okay, is the only even prime number there. 1 divided by 15 is going to go in the numerator. The probability of C, there's 6 things in C out of 15. Okay, so 6 out of 15. Flip the denominator. The 15s are going to cancel there, so 1/6. Okay, and remember, again, your sample space is always reduced in size whenever you're computing a conditional probability. So the probability of A given C. So we're given C, these 6 numbers. What's the probability of A given C? 2 is the only even prime number, so 1/6. Like, we could have went right to the answer there. Okay. Problem 43. A family has 3 children. What is the probability that the youngest is a girl, given that there are at least 2 boys? Okay, at least 2 boys means 2 boys or more. Okay, so the one girl can be born either first, second, or third, or all 3 of the children are boys. They have at least 2 boys. So what is the probability that the youngest is a girl? A girl born last means that the youngest is a girl. So 1 out of 4 is my answer. I don't see any other elements there with a G listed first there. Okay. Problem 44. According to the U.S. Bureau, 19.1% of U.S. households are in the Northeast. In addition, 4.4% of U.S. households earn $75,000 or more per year and are located in the Northeast. Determine the probability that a randomly selected U.S. household earns $75,000 or more given that the household is located in the Northeast. Okay, given is a key word. Okay, so if I write that down, the probability of the house earning $75,000 or more, given that it's located in the Northeast. Okay, so the fact that that's a key word indicates that I've got a conditional probability, so I'd want to use the conditional probability formula. The probability of selecting a house that's $75,000 or more and located in the Northeast, divided by the probability of it located in the Northeast. Okay? Remember, whatever event you're given, you're going to be dividing by the probability of that event in the formula. Okay? So I'm going to be dividing by the probability of the house being located in the Northeast. And I'm told these two things here. So the probability of the household being located in the Northeast, well, 19.1% of U.S. households are in the Northeast. Okay, so 0.191. Go in the denominator. The probability of it earning $75,000 or more and located in the Northeast, well, that's this statement here, right? 4.4% of U.S. households earn $75,000 or more and are located in the Northeast. Okay, so 0.044 divided by 0.191 is approximately 0.2304. Okay. By the way, one thing to mention here, so the notation is important. Okay, I see more than I should, actually, where a student will just write probability of 75,000. That's not what we're computing. We're not computing the probability that, in fact, we're not told that, right? We're not told the probability that that the U.S. household earns $75,000 or more. We are told that it's the probability that the household earns $75,000 or more per year and is located in the Northeast. Okay, so I guess what I'm trying to say is that it is important that we write the given Northeast. Okay, otherwise it doesn't mean the same thing. It's not going to equal the same thing. Okay. Problem 45. Suppose that two cards are randomly selected from a standard 52-card deck. What's the probability of getting a club second given that a diamond was selected first? Okay, a club second given that a diamond was selected first. Given is a key word. So I'd want to use the conditional probability rule. Probability of getting a club second and a diamond first divided by the probability of getting a diamond first. Okay. Well, the probability of getting a diamond, there's 13 diamonds in the deck, so 13 over 52 would be in the denominator. Now, what if we get a club second and a diamond first? Well, that's the same as getting a diamond first and then a club second, right? If we look at it like that, the probability of getting a diamond first, 13 over 52, is what I just said, times the probability of getting a club second. Well, now you've already selected one card that is a diamond. Okay, so there's going to be 51 cards left in the deck. All the clubs are still there, though. Okay, all 13 of them. So I'd multiply by 13 over 51. The 13 over 52s are going to cancel, leaving you with 13 over 51. By the way, I think they should make total sense to us. Okay, so the probability of getting a club second, given that a diamond was selected first. Well, if we select a diamond first, there's not 52 cards left in the deck anymore. Right? There's 51 cards now. All the clubs are still there, all 13 of them. So 13 over 51, boom, we could have went right to the answer. 46, a pet store has 7 puppies, which include 4 huskies, 2 terriers, and 1 retriever. Rebecca and Madeline each select a puppy. What's the probability that Madeline selects a terrier given that Rebecca selects a husky? Okay, so the probability of getting a terrier second, given that a husky was selected first. This is a conditional probability, so I need to find the probability of getting a terrier second and a husky first divided by the probability of getting a husky first. Well, there's 4 huskies, right? So 4 divided by 7 would go in the denominator there. Probability of getting a terrier second and a husky first is the same thing as the probability of getting a husky first and a terrier second. Okay, since you're still talking about the same overlapping region on the Venn diagram. So 4 over 7 is the probability of getting a husky first. And then, let's see, there's 2 terriers. Now, if somebody already selected a husky, there's 6 dogs left. Okay, 2 terriers. So the 4 over 7s would cancel, leaving me 2 over 6, or 1/3 would be the answer. Okay, again, I think this is something that we could have went right to the answer to with. So if I was told that somebody's, like, there's 7 puppies at the store, and somebody's already selected a husky, well, there's not 7 puppies now. Okay, there's only 6. Okay, and I want to select a terrier. There's 2 terriers, 2 over 6, reduce that, 1/3 is the answer. Okay, so the homework in section 11.3 is on page 633. Be sure to look at those problems for me when you get a chance. And 11.5 is the last section that we'll take a look at, which is a section on expected value. Definition, if a random variable x can have any of the values x1, x2, x3, all up to xn, and the corresponding probabilities of these values occurring are the probability of x sub 1, probability of x sub 2, etc., then the expected value of x is given by e of x equals x sub 1 times the probability of x sub 1 plus x sub 2 times the probability of x sub 2 plus etc. plus all the way up to x sub n times the probability of x sub n. Okay, so you're going to take each value times the probability, in other words, to compute an expected value. On problem 47, it says a popular casino table game is 3-card poker. One aspect of the game is the pair plus bet, in which a player is paid a dollar amount for any hand of a pair or better, regardless of the hand the dealer has. The table shows the profit and probability of various hands of a player playing the $5 pair plus. Okay, so here's our table here. Part A, what is the expected profit when playing the $5 pair plus bet in 3-card poker? Okay, so using the formula up here, I'm going to take each value, which is the profit, the dollar amount, times the probability. Okay, so the probability of getting a street flush plus the probability of getting a 3-card, three of a kind, plus the probability of getting a straight, plus probably getting a flush, plus the probability of getting a pair, plus any other. Okay, and so if I enter that in the calculator, which I can type in the whole thing all at once if I want to, I end up getting negative 0.12. Okay, so what that means to me is that if I played this game over a long period of time, the average loss would be 12 cents per hand. Okay, so that's nice to know. If if somebody were to sit at the table and play this card game for ever and ever, they would be losing money. Part B, if you play the game for 4 hours with an average of 35 hands per hour, how much would you expect to lose? Okay, so we take our expected loss, negative 0.12, times 4 hours, times an average of 35 hands per hour, times 35. That gives us negative 16.8. Okay, so $16.80 would be how much we'd lose, or expect to lose, during that 4-hour time span. Okay. Problem 48 says 1,000 tickets are sold at $1 each for a flat screen TV valued at $350. What is the expected value of the gain if you purchase 1 ticket? Okay, so if you purchase 1 ticket, you're going to lose $1. Okay, since each ticket costs $1. 999 people are going to lose this game out of the 1,000. Only one person's going to win. Okay, so the person that won would have won the equivalent of $349 since it costs $1 to play. You're not winning $350. And the probability of winning would be 1 over 1,000. Okay, if I were to type this in to the calculator, negative 0.65 would be the expected value. Okay, I'm going to note here, this does not mean that you lose 65 cents, since you can only win a TV valued at $350 or lose $1 on the ticket. Okay, like nobody lost 65 cents. Okay, what this expectation means is the average of the losses is 65 cents for each of the 1,000 ticket holders. So it's like everybody lost 65 cents. Okay, for this one person to win a TV. Okay. Problem 49 says that in a certain card game, suppose that all 13 diamonds are removed from a standard 52 card deck and are placed in a bag. One card is randomly selected from the bag. The player wins according to the following rules. So if an ace is drawn, the player loses $20. If a face card is drawn, the player wins $10, and if any other card, 2 through 10, is drawn, the player wins $2. How much should be charged to play this game in order for it to be fair? Okay, well, for it to be fair, that would mean that neither the dealer nor the person playing is losing money. Okay, so this comes down to calculating an expected value. Okay, so take each value times the probability. There's only 13 diamonds that we're playing with. So the player is going to lose $20 if an ace is drawn. Only one of the cards is going to be an ace. Okay, and of course I want a negative number there since that's a loss. Okay, and then we're going to gain $10 if a face card is drawn. So a face card is jacks, queens, and kings. Okay, and then if any other card 2 through 10 is drawn, the player wins $2. Okay, so 2 through 10, there'd be 9 cards out of the 13. You're going to win $2. Okay, so what this comes down to is $2.15. So because it's expected that a player would win $2.15 per game every time he or she plays, the house would want to charge $2.15. This way, neither the player nor the house is expected to lose in the long run. Okay, and that's what will make the game fair. Okay. The homework in this section is on page 653. Be sure to look at the problems there when you get a chance for me. And we're now done with chapter 11. We've got 2 more chapters left, chapter 13 and chapter 14. We're going to do chapter 13 next, so stay tuned for that.